Hello and welcome to our presentation of second phase EL chemistry. My group members are Arpit Verma, Pritish Raj, me Varnit Shree and Vignesh Kumar. The topic that we chose is storage of hydrogen using metal organic framework. So the first question that arises when we hear the storage of hydrogen is why do we need to store hydrogen in the first place? First of all, decreasing amount of fossil fuels and high amount of pollution caused due to their high rate of carbon emission, hydrogen is the best replacement as it has energy density much greater than that of daily use fuel gasoline and almost 3 times higher energy content compared to gasoline. Slight change. Hydrogen is abundant available but it's generally available in compounds and requires separation. Hydrogen is also an energy carrier and not just an energy source. Hydrogen storage is the key to enabling the full potential of hydrogen. Hydrogen will also be a way cleaner alternative to everyday fuels like coal, petrol, etc. Slight change. But there are some prerequisites to hydrogen storage. There are numerous materials being tested. The main requirement is to find a material that absorbs H2, great H2 density, greater than that density of liquid H2, as liquid hydrogen takes very little space, almost 70.8 kg per meter cube at 20 Kelvin at atmospheric pressure. As you would already know, there are many advantages to hydrogen as well, which we'll show in the next slide. Next slide, please. Advantages to hydrogen. It is present abundantly, just requires separation from its compounds. There is almost no greenhouse gas emission or residue from hydrogen combustion. It can also be collected as byproduct of chloroalkali industry, which is a very easy way of obtaining it. And hydrogen usage is cleaner when water or solar energy is used in production process. With pros come some cons, and we'll discuss the disadvantages of hydrogen in the next slide. And hydrogen, like any other thing, has its cons. Hydrogen extraction is extremely expensive, and the separation also requires the burning of coal or oil, which has carbon emissions to add to that of hydrogen. And it's very difficult to store hydrogen and to detect leaks. We have to ensure sensors which can be faulty and not reliable and cause leakage. To summarize, hydrogen storage is possible, but we need to be careful. Over to Pritish.
Yeah. So now moving further, we will first understand some of the terminologies related to hydrogen capacity. The first of the definitions that we need to understand is adsorption and absorption. So the absorption is a process when absorbates are absorbed inside the internal structure of the adsorbent. In this process, structure or the chemical formula may or may not change, and it is a bulk phenomenon. Whereas adsorption is a process of enrichment or depletion of one molecule into another at its interfacial layer. It is a bulk phenomenon. Now, the second of the term that we need to understand is sorption and desorption. So, the sorption is a term that is referred when adsorption and absorption both takes place simultaneously. On the other hand, desorption is a term that refers to the opposite of sorption. Both sorption and desorption of the absorbate by the sorbent is a dynamic process. Next term to understand is chemisorption and physiosorption. So chemisorption is a surface phenomenon that happens only when the interaction force between surface and adsorbate is similar to that of chemical bonding, whereas physiosorption is a process that is limited to adsorption and happens when intermolecular forces are weak enough to bind them together. We need to understand one difference over here, that chemisorption is a monolayer process while physiosorption is a multi-layer process. Chemisorption occurs at low temperatures and releases less amount of energy, whereas physiosorption occurs at high temperature and is associated with huge amount of energy. Next term to understand is excess and total adsorptions of hydrogen. Hydrogen absorbed in the surface is under very high pressure, and it is represented as excess and total adsorption of hydrogen. This excess hydrogen that is absorbed is called Gibbs excess, which is nothing but the difference between the amounts of gas phase that would be present in the equivalent volume of the adsorbed phase. Mathematically, we can understand it by the formula as V pore is equal to 1 by d times of bulk minus 1 by d of skeletal, where V pore is the volume of the pore in centimeter cube per gram. D bulk is the crystallographic density of the sample, and d skeletal is the skeletal density of the material, which is given as m by v of a skeletal, where m is the sample mass expressed in gram and v skeletal is the sample volume in centimeter cube. Last term to understand is the isostatic heat of hydrogen absorption. It is the amount of heat associated with interaction energy between hydrogen molecules and the MOFs. It is generally calculated at adsorption isotherm at two independent temperatures, mainly at 77 and 87 Kelvin. Please next slide. So moving further, first we will understand some of the basic hydrogen storage techniques that are present right now. So one of the most common way is to store hydrogen is to store it in cryogenic containers, but it has some of the disadvantages as to maintain as to store hydrogen in a temperature of minus 40 to 60 degrees Celsius in passenger vehicles is quite tough, and it also exponentially increases the price of the vehicles. And moreover, at 700 bar, hydrogen's volumetric energy density drops to is very low as compared to the gasoline having gasoline's energy density. Next slide, please. So now we will see some of the technological advancements in the field of MOFs, that is metal organic frameworks. So the person Kitwaga et al. Was the first in 1997 to observe adsorption on MOF. Since its time, there are various experiments and going on in these topics. So we will now see various types of MOFs. Please next slide. So first we will see carboxylate based MOFs. So these MOFs are synthesized by the process called solvothermal reaction, in which metal ions react with various carboxylic acids. The use of rigid organic carboxylic acids in the manufacturing of MOFs result in its exceptional robustness, and many times it does not even collapse after the removal of foreign solvent. After conducting various experiments, it can be said that properties of MOFs slightly depend on the type of metal used, but it mainly depends on the surface and porous size of the framework of MOFs. Some of the carboxylate-based MOFs are air sensitive and thus proper handling is required. Examples are zinc carboxylate-based MOFs, which are air sensitive, and its hydrogen capacity decreases upon exposure to air, hence it needs to be handled carefully. Next slide. Now we will learn about azolate-based MOFs. So imidazole, pyrazole, triazole, and tetrazole are called heterocycle ligands that are used in the synthesis of porous MOFs, and these are used as a ligand for metals. So these classes of MOFs have thermal and chemical stability. The most important thing about these MOFs is that it is stable in air, boiling water, and even acidic medium. So here I will make a focus on two types of triazoles, namely 1,2,3 triazole and 1,2,4 triazole, because these triazoles depend on the position of the N on the rings, that is nitrogen on the rings. Next slide, please. Now we will see another type of MOF that is prepared with the help of mixed ligands. So we can prepare MOF when we use two or more type of ligands together. And it is not necessary that we should use two different ligands only. If we use one ligand that have two different sites that could donate, then that is also an example of the MOFs with mixed ligands. A typical example can be pyridyl carboxylic acid such as isonicotonic acid and pyridine dicarboxylic acid. Now, next type of MOFs are MOFs with metal complexes and building blocks. It can be further grouped as two macrocyclic and metal cyanide frameworks. So, macrocyclic complexes based MOFs are those MOFs in which there are more than in which we use linear dicarboxylic, trigonal tricarboxylics, or tetrahedral tetracarboxylics carboxylates. So the advantages of these MOFs is that they can form various grooves in the structure. Another type of MOFs are known as metal cyanide frameworks, which are prepared when metals are reacted with different types of hexacyanode metallate. The example is as shown here Cu3CO Cn whole 6 whole twice, which is synthesized from K3CO Cn whole 6 and CuNO3 in an aqueous medium. Next slide, please. Now, once we store the hydrogen, we should have some of the technologies to measure it. So the conventional method that we use is thermogravity, which determines hydrogen capacity. Its major disadvantage is that if there is any small amount of water present in it, it could result in a big error. So nowadays, due to this error, we use volumetric method, which is used to determine hydrogen storage capacity, which works on the principle of change in the pressure of hydrogen during adsorption or desorption in a closed chamber. Now over to Vignesh.
Now let's discuss about materials and methodology. The first subtopic is a metal organic framework MOF 76 neodymium. The chemicals used in preparation of this MOF are neodymium nitrate, a benzene 1,3 dicarboxylic acid, N, and dimethyl formamide, and ethanol, uh, which are which are selected with the highest existing purity. Let's discuss about synthesis. 50 grams of neodymium nitrate and 20 milligrams of benzene 1,3 tricarboxylic acid are dissolved and, and mixed in a mixture of solvents with ethanol, DMF, and water. The reaction mixture is heated to 80 degrees Celsius for 1 day and cooled to ambient temperature at, at a rate of 2 Celsius per minute. The MOF, which are violet needle-shaped crystals, are filtered and washed off with ethanol. Further, these needle-shaped crystals are dried in a stream of air which yields 96% based on benzene 1,3,5 tricarboxylic acid. In this, we are mainly going to discuss about hydrogen storage measurements and humidity sensing measurements. Coming to hydrogen storage measurements, a high pressure hydrogen absorption or desorption method is followed by a CVOT type setup. Next slide, please. Next slide. Humidity sensing measurements. Humidity sensing characters of MOF76 neodymium are measured by a ceramic substrate having silver palladium integrated electrode. The next subtopic is how can we achieve record high hydrogen storage capacity in metal organic framework at ambient temperature. In this, we are mainly going to discuss about nickel M.DC, cobalt M.DC, and hydrogen. So we are mainly going to consider the synthesis of hydrogen M.DC. The main component or isocyanates is pulverized and dried under vacuum along with KHCO3. These two are mixed thoroughly, which is sealed in a part reaction bomb, which has an internal thermocouple and pressure gauge. The reaction bomb was evacuated under vacuum, and carbon dioxide is maintained at a pressure of 40 bar. The bomb was heated to 250 degrees Celsius in a sand bath for 1 day and cooled to room temperature slowly. Later, 1 liter of water is added, which is broken up mechanically and sonicated. The resulting suspension is filtered and the filtrate is acidified with HCl until pH is less than 2 is achieved and white solid is precipitated. This solid is collected by filtration and dried to yield 79% efficiency of the product. Next slide. So here we are going to see two pics. A is the wave, A is the TEM images of MOF76 neodymium uh, of 6 micrometer and B is of 100 nanometer. And coming to the second pic, it is a wave of the building blocks of uh, metal organic framework 76 neodymium polymeric framework. Next slide. Next subtopic is exceptional hydrogen storage can be achieved by screening of a million of metal organic frameworks. The most promising MOFs that can be achieved are CNU70, PCN610, and UMCM9. So let us consider the synthesis of SNU70. E4,2 carboxyvinyl benzoic acid and zinc nitrate are dissolved. Six such reaction mixtures are heated to 105 degree for 12.5 hours and cooled at a room temperature. The precipitate is removed from the MOF by washing multiple times with DMF and the remaining crystals are collected together in a glass vial soaked in DMF. Next slide. Next, synthesis of PCN16 or NU100. 1,3,5 tris 1,3 carboxylic acid, 5,4 ethynyl phenyl ethynyl benzene, and copper nitrate are dissolved in DMF. Hydroboric fluoric acid is added to the solution and the color of the solution until the color of the solution is turned to teal. The solution is divided into 34 ml vials and the vials are heated to 75 degrees Celsius for 20 hours. Teal colored octahedral crystals, which are formed at the bottom of the vial, are collected. The MOF is immersed in ethanol for another day and the liquid is replaced with fresh ethanol. The compound is activated by flowing liquid carbon dioxide at a flow rate of 2 milliliter per minute for 1 hour. Subsequently, the supercritical carbon dioxide at 2 milliliter per minute flow rate for 2 hours at 55 degree and finally supercritical carbon dioxide at 1 milliliter per minute for 6 hours to result from a purple solid. Next, synthesis of UMCM9, naphthalene 2,6 dicarboxylic acid and 1,1 biphenyl 4,4 dicarboxylic acid, DEF and N-methyl pyrroline are dissolved in solvent mixture by sonication. Zinc nitrate is added to the solution and the mixture is sonicated until transparent solutions are obtained. The reaction mixtures are heated to 85 degree for 4 days. Cubic crystals of the MOF are formed at the inner surface of the vials. After cooling at room temperature, the liquor is decanted and the precipitate is removed by washing multiple times with DMF. Later, they are collected together in a different vial. These crystals are immersed in DMF for 3 more days, then in dichromethane for 18 hours, finally in dry hexane for 12 hours. Finally, the material is activated under vacuum for 26 hours to yield clear pale yellow crystals. Over to Arpit.
So here are the conclusions that we have drawn from the research papers that we studied. Looking at the future, hydrogen is going to be one of the most important players in building a green economy. Hydrogen is green fuel and it doesn't cause any pollution. Hydrogen, however, has highest energy by mass ratio of any fuel, and as a result, storage is a tedious job. Here is where MOFs can be helpful. MOFs have many advantages, like they are highly porous, they have large surface area, which can be useful in hydrogen storage. Researchers have found that MOFs that have high porosity can be used to store hydrogen. As it is still early days, many researchers have told that hydrogen does that MOF do decent job to store hydrogen at 77 K and moderate temperature. One problem that MOFs encounter is that they they are hydro that they are sensitive to water. This problem can be tackled by adding a hydrophobic group, which can increase the efficiency of MOFs to store hydrogen. An- Another way of increasing the efficiency is by adding foreign substances like palladium, or even processes like calcination and washing as they finish off the impurities. One method that can help in increasing the efficiency is catenation, which reduces the free diameter of pores. Another method is impregnation, which is the insertion of adsorbate sulfate within the MOF. MOFs have good efficiency at 77 Kelvin. However, lot of work has to be done to see how they perform at ambient temperature, because the interaction between hydrogen and MOF is very weak at higher pressure. One more method which can be used to increase efficiency is adding cations like magnesium plus 2 and aluminum plus 3, as they give rise to strong coordination bond that protect against hydrolysis. The future scope of MOF is immense, as lot of more materials will be discovered which are high in efficiency and low in production cost, and they're one of the hottest topics to do research on. In future, machine learning can also help us with the goal of having efficient hydrogen storage in MOFs. Here is the here are all the references that we have used for our uh, EL project. Thank you.